Next, we are going to see a few axioms that are going to be used throughout this course. To begin with, let's consider the set of natural numbers. That is the set of 1, 2, 3, 4, and so on. And the cardinality of this set is of course infinity, but one important thing about this set is that the elements are ordered, linearly ordered. In the usual sense, we have 1, which is less than 2, which is less than 3, which is less than 4, and so on. So we have this linear order among the elements of the set of natural numbers. Now, let's introduce one axiom here. It's called the principle of well-ordering of natural numbers. Well-ordering of the set of natural numbers. Suppose S is a non-empty subset of natural numbers. S is not empty. Then there exists a least element in S. For any subset, non-empty subset of natural numbers, there is a least element. Okay, so we state this as an axiom. Okay. The least here means least in this sense, in this order, in the usual order of numbers. And for stating some theorems or problems that contain some dependence on a natural number, we write P of n. So this is a statement, logical statement involving a natural number n. Okay. For example, we have this formula, which I think you are familiar with. The sum of natural numbers from 1 to n is equal to this: n times n plus 1 divided by 2. Okay, so this equality holds. So this equality itself may be cast as a logical statement Pn. So this statement depends on this n, and it's a logical statement because it's the left hand side is equal to the right hand side. So whether this is true or not is a logical statement. It's a logical proposition. Okay. And another example is, for example, is like this: 2n plus 1 is less than or equal to 2 to the power of n for any natural number n. This is another example, and you should prove it. Next, we introduce the principle of mathematical induction as a theorem. Is a theorem. Induction. Okay. Let P n be a proposition. Logical proposition depending on n. And suppose the following two conditions are satisfied: P of 1 is true, and 2, if P of k is true, then P of k plus 1 is true. Okay, then P of n is true for all natural numbers n. Okay, so this is the principle we use to prove many theorems. That is the mathematical induction. But this is a theorem here, and we are going to prove this. Now, here's the proof. First, we define a subset of natural numbers. Let's say S is a subset of natural numbers such that the proposition P of n is true. Okay, what we are going to show is that this subset S is actually equal to the set of natural numbers itself. So what we want to show is this S is equal to n. Okay, so this is to be shown. Now, by assumption 1, this one, so we are assuming P of 1 is true. So by condition 1, 1 belongs to this subset S. Therefore, S is not empty. Okay, this is at least, this S contains at least one element, 1. Now, let's define the set X as the difference between the set of natural numbers and this S. Okay, we want to show that this set X is empty. And to show that, we prove this by contradiction. Okay, so suppose this X is not empty. Then there are some elements in X, but by the principle of well ordering, there exists a least element in X. Okay, so let M be the least element. Least element in X. So since M is the least element, then P of M minus 1 is true, right? In other words, since M is the least element of X, M minus 1 does not belong to X. Right? Otherwise, M minus 1 is less than M, so this should be less than the least element, which is a contradiction. So this cannot happen. But since M minus 1 does not belong to X, it means that the proposition P of M minus 1 is true. Right? However, but by condition 2, if this is true, then P of k is true, then P of k plus 1 is true. So now this k is M minus 1. So we have this true proposition, P M must be true. But this means Therefore, M must belong to S, right? Because S is the set of all natural numbers such that P of n is true. So P of M is true, then M should belong to S. But by definition, M is an element of X. But 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 X is defined as this. So X cap S is empty. So no element can belong to both S and X, which is a contradiction. So our assumption was wrong. And here our assumption is this. X was non-empty. Therefore, X is empty. Therefore, S is equal to the whole set of natural numbers. And we are done. From this proof, you can see that the principle of mathematical induction is based on the principle of well-ordering of natural numbers, right? In the proof, we have used the principle of well-ordering here. Anyway, we can extend this principle of mathematical induction to a little bit more general form. That is, we can actually prove it, but rather than proving it, we just accept it as an axiom. So here it is. Again, P of n is, let P of n be a proposition, logical proposition. Depending on n, which is a natural number. And suppose 1, P of 1 is true. 2, if for each m less than k, P of m is true, then P of k plus 1 is true. Then P of n is true for all natural numbers. Okay, so the difference from the previous version is this part for this one. Previously it was just P of k, but here it is all natural numbers less than k or equal to k. So if this is true for all natural numbers less than or equal to k, then P of k plus 1 is true. Here's an exercise. Show that 2n plus 1 is less than or equal to 2n for n greater than or equal to 3. Of course, n is a natural number. This may not be true for n equal to 1 or 2. For example, when n is equal to 1, the left hand side is 2 times 1 plus 1, that's 3. And the right hand side is 2. So this doesn't hold. When n is equal to 2, the left hand side is this, which is 5. And the right hand side is 2 to the power of 2, which is 4. So this is not true. What about when n is equal to 3? So that is 7 and 8. So this is true. So for general case, you should try to prove this one.